At any one time, over 500,000 people are travelling in the air. 10,000 litres of jet fuel are burnt every second. This accounts for 2% of world CO2 emissions.
When you board a plane, what you see are the huge fan blades at the front of the engine, but behind these, the compressor squeezes the cold air to a 20th of its volume and over 600 degrees centigrade. Then the fuel burns, and that raises the temperature even higher to 1800 degrees just as the gas enters the turbines. The turbine extracts the energy to drive the plane.
In the development of a new large civil engine, the most important factors are fuel burn or engine efficiency, and that's important for both the environmental performance, the emissions from the engine, and also the economic performance in terms of the operating costs. In order to make an aero engine more efficient, there are really two factors. There's the propulsive efficiency driven by the fan, and there's the thermodynamic efficiency driven by the core of the engine. So what you really need are lightweight materials for the fan and high temperature, high strength materials in the core of the engine.
If you could look into the turbine, it would be glowing white hot. And this minute, 500,000 people are hanging in the air by metal that should be molten. We're only able to keep the blades solid by clever engineering. We feed cooler air over the surface of the blades, and we add ceramic coatings to insulate the metal. To make more efficient engines and to reduce the carbon footprint of flying, we need new materials that can operate at even higher temperatures.
Jet engines have always been limited by the performance of the materials, and in particular the high temperature materials at the core of the engine. So for Rolls-Royce to remain competitive with competitive products in the marketplace, we must have access to the absolute best materials technology. The work that we do with Cambridge is very technically complex, designing alloys from atoms up and proving their performance for service.
We've reached the limit of our existing materials, so this is our grand challenge.
It's a grand challenge because of the requirements placed upon the material. Not only must they withstand temperatures hotter than molten lava, but simultaneously sustain enormous mechanical loads.
At takeoff, the engines are spinning at 12,000 RPM, and the tips of the turbine blades are traveling at more than 1.5 times the speed of sound.
The stresses experienced by each blade is equivalent to hanging 15 hatchback cars at the end of each one.
Each turbine blade generates more power than a Formula One racing car.
And they need to endure these conditions for tens of thousands of flight hours.
The sustainability of each metal is also critically important. We cannot design new materials that contain metals that are scarce or come from areas of conflict.
We need to account for all these factors when designing new materials.
The new materials we're interested in designing are new alloys. Alloys are mixtures of metals, sometimes with some non-metals thrown in. Almost all the metallic materials we use day to day are alloys. The most widely used alloy is steel, which is an alloy of iron and carbon, but other common examples include copper alloys like brasses and bronzes. The alloys we use in jet engines are called super alloys. They're very special alloys that we create by mixing different elements in nickel. They're called super alloys because they have exceptional properties, particularly at high temperatures, so great high temperature strength and resistance to corrosion.
When we look at alloys on the atomic scale, it turns out that all the atoms are arranged in a regular plane or array. This is actually what defines something called a crystal, and there are many examples of crystals all around us. Things like quartz, diamonds, emeralds, but in fact also things like salt and sugar. Different alloys will have different atomic compositions in them and a different arrangement of the atoms in the structure. It's a bit like making a cake. It requires the same basic ingredients, but actually by changing which ingredients you use and the quantities you use them in, we can change the type of cake that you make.
We build alloys from the ground up, starting by deciding what elements we want to use in the alloy by using the behavior in previous alloys.
For example, chromium is added for corrosion resistance. This is what makes steel stainless.
Once we have decided on the precise quantities we would like to use in the alloy, we then weigh out each element individually and melt everything together to form a bar.
Once we have our alloy, we can then thoroughly investigate it for its properties. This usually involves a heat treatment in the furnace and preparing it for studying in the microscope.
Using transmission electron microscopy, We're able to map these alloys right down to the atomic scales and evaluate the contribution of each of the elements towards the structure and strength of these materials. We test our alloys at every step along the process. This goes from the moment we make those alloys all the way to testing their mechanical properties. We need to make sure that those alloys have the right structure to have the best mechanical properties, as well as making sure that they are stable over a long time at high temperature. This is how we guarantee that the alloys we make are safe to use and safe to carry people.
So the way the atoms are arranged directly affects the way the engine performs. So to solve a global engineering challenge, we need to arrange atoms to produce even better materials. If we can arrange the atoms, we can control the properties and produce safe, sustainable air travel in the future.